The other thing is, so today we're finally getting into some grad level stuff. So we're going to start on questions, problems that are not, we don't do it undergrad level. And it's way, way more interesting. We're going to do a problem that's going to seem impossibly hard, and it involves delta functions, and delta functions are my favorite thing ever. And because of that, you're going to like delta functions too, because they take all the difficulty and it all just gets wiped out. It's unbelievable how quickly these problems get made way more simple with delta functions. Also, we're going to do some computer stuff. So last time I mentioned, I started mentioning a scattering phenomenon, which would basically take the particle in a finite box and flip it over. Reviewing my notes, actually I want to end on that. And again, that's not really a traditional undergrad level course. What I want to do is scattering. This pin worked a second ago. I do not get this. I checked this pin 1 minute ago. I have no idea how that just happened. That's interesting. This pin doesn't work, I guess. I guess you got an extra hour to finish that homework. There we go. Okay, so we're going to do scattering, and scattering is one of the most important things that you ever use quantum for. And remember, this is something hitting something else, which is like, oh, well, when am I going to study that? Actually, all the time. Almost every chemical phenomenon can be looked at, something running into something else. And I want to start simple. So let me draw the potential surface. We're going to have a wave moving to the right. So that's an A wave. It'll scatter off the potential, and that'll be the backward wave, the B wave. And we'll have a transmission through the potential, which will be a C wave. So we've got our psi 1, our psi 2. What I'm not telling you is what is the potential. Delta function. We're going to hit an infinitely high, yet infinitely thin barrier, which is kind of like really messing with your mind, right? If it's infinitely high, you're not going to pass through that. But it's infinitely thin, so maybe you can. But it's infinitely high, so you can't. But it doesn't have any width, so you never messes with you, right? So anyway, so our potential energy is going to take the form. Now, I'm going to add some constants here. I'm adding a bunch of constants because this just simplifies the problem. H bar is still H bar, m is the mass, and of course it'll be mass of an electron. Gamma will be, or whatever the hell, what is that? That's capital gamma, right? I don't know what that is. No, that's omega. That's omega, it's capital omega. Okay, these don't have any purpose except just to make the problem easier. Okay, but the real deal is the delta function. Okay, so there we go. Infinitely high, so it's got to do something, but it's infinitely thin. So it can still get through it. Okay, so we're going to have an A wave and a B wave. So we assume that the electron hits it and then it'll bounce off. That's why you have a B wave. We know that e to the minus ikx goes backward. And in region 2, we're going to say that if you get past the delta function, that you just continue on. There's nothing else, you're not going to do anything else, so there's no reason you're ever going to jump backward. Now again, this is definitely a graduate level type problem, and it ends up being way easier. And by the way, one of your homework problems is basically just like this. So I'm kind of doing one of your homework problems, except that instead of being a barrier, the delta wave is actually the potential, and you solve for energies less than 0. That's a hint on your homework, by the way. Remember, you watch the video if you don't remember the hint when you're doing it. And so as usual, right, we try to choose a judicious coordinate system. So of course we're in X. 0 is where the barrier is. There's our wave functions. And yeah, anyway. All right, so what do we do? So now we're just going to solve this guy because, again, it's a nice exercise and it's a good lead up to scattering. So I'll do, I would say, we're going to do a finite barrier at the end of the last class, but I'm going to actually do two problems, two actually kind of smaller problems, and then we'll do that last. And by do that last, remember I told you that the answer is actually, I worked through it and it's on the website. Anyway, okay, now, as usual, there's always some kind of trick that's like, where'd you come up with that? Well, because I read it in a book or I found it online, that's how I figured it out. We can set A equal to 1. So, sorry, I should back up. Big picture, you know, so you've been given a problem, and here it is. So what do you do with it? So, the first thing is to solve the wave functions. So there's our A wave, and there'll be a backscatter wave. So there's our B wave. So we got to solve A, B, and C. Once we have those, then we can figure out what the energies are or whatnot. We can also figure out the reflection and transmission. The reflection would be the magnitude of the B coefficient, and the transmission would be the magnitude of the C coefficient. That would be the wave function, the wave function squared, the absolute value of the wave function, but a complex part always, the absolute value of EBIX is 1. So hopefully you know that at this point intuitively. To go about it, we said A equals to 1. Now one reason that works is, as I mentioned, we set up the problem, we solved A, B, and C. Remember that normalization would be the last step. So let's not worry about normalizing it. And if I'm not worried about normalizing it yet, I'm just trying to get to some of the innards. I'm just trying to get to the relative of magnitudes of A, B, and C. I'll normalize it some other time, and then I'll know exactly what they are. But for now, I can just I can make one of them whatever I want. So I'm going to make A 1. Notice that I'm going to end up with two equations, smooth and smooth and continuous at the boundary. So two equations, and I have two unknowns, B and C. So this is going to happen. So this will work. One reason to set A is that if I don't, then it seems like I have three equations, three unknowns and two equations, and that doesn't work. Anyway, okay, so now what? Okay, so now so that's number 1. Number 2, these are the steps. So let's say it's continuous at x equals 0, and therefore A e to the I 0 is A, plus B e to the minus 0 is B. Make sure I'm doing this right before. Is equal to the other wave function, C e to the 0 is C. Oh, that's right, A is 1. So 1 plus B is equal to C. Okay. One equation. Now I just need the other one. This is the cool part, right? So now you're in grad school. Let's do the derivative. Okay. Actually what we're going to do is set up the Schrodinger equation. So actually I think I misspoke. So the funky thing about this is, I think it is continuous. I don't think it's smooth. Because I've been telling you, especially you two that took my class, wave functions have to be smooth and continuous, and we use those to solve those other problems. But a delta function is actually that's a deal breaker. That's going to be a deal breaker for this. And anyway, so there's that. All right, so what do? So set up the Schrodinger equation. All right, so let's do that. And let's see what that buys us. And what's great about this problem, I think you'll appreciate the mathematical gymnastics you can do. So I think you'll think this is kind of cool. So there's the kinetic energy. Let me go ahead and just put the potential energy over here. Let me just go ahead and plus potential energy equal energy times wave function. So I've done a little bit of algebra there. Okay, next thing is I'm going to, for various reasons, you'll see in 1 second, I just want the double derivative of the wave function. So now I've got 2me over h bar squared. And so there's my k, right? The potential energy is flat, right? And I don't have a barrier except for this infinitely thin thing. So this is what we have traditionally called, actually that's k squared, right? That's k squared, sorry. Okay, now let's insert this odd potential energy. And you can see why I threw in some constants just for the hell of it. The omega can kind of wipe those out. I threw those constants in just because the problem turns into this form. It's just a hell of a lot easier. Dirac delta function, and I love delta functions. I've said that many times. And of course, these are all multiplied by the wave function. Okay. Now what we do is we integrate both sides. Now this is the trick, right? There is nothing better than a delta function inside of an integral because there's no more integral. So that's why this problem is kind of awesome. Okay, now, so let's do that. Let's see here. I am going to integrate, let's integrate this guy. Now, all the action is at 0. So there is no point to integrate it anywhere else except at 0. So to do that, I'm going to do a limit. I'm going to integrate this to the left and right of 0. Left of 0, right of 0. And I'm going to integrate it in a very, very narrow range, right at that delta function. One reason to do this is that the delta function is the only thing going on. Let's put it that way. I can't imagine why I would be doing any maths anywhere left or right of the potential because the potential is like the only thing there. So I'm going to integrate it right at the potential. Maybe you can just think of that as, well, that's the trick, right? There's always a trick. Okay, now what is that? Okay, now before you thinking like, well, oh my God, the integral of e to the x. No, this is actually way easier. The integral of a double derivative is a single derivative. Let's take the upper limit. I should put the limit. Whatever. Yeah, I should do that. Sorry. Let me add now. I'm feeling like I'm not being careful enough. Okay, so the limit of the single derivative of x. Make sure again I'm doing this right. Epsilon. So that's the upper limit, and then you subtract the lower limit. So there you go. Okay, so that's the left half. And what this does, it heads up on this. This is going to give us some these gives us our coefficients. So we can do some work with that. Let's do the other side. Let's do this part. Okay, what do we got there? Okay, so this is the integral of minus, I gotta put that one down. I feel like if I don't do it, I'm doing something wrong. Okay, so again, we've applied, we're going to integrate over a very narrow region. And what are we going to integrate? We're going to integrate, I will define this. So here is our delta function minus k squared and remember that k squared is 2me over h bar squared. Again, hopefully at this point you're every time you see a k, this is just going to come out naturally. At this point, I hope so. Okay, now what does this turn into? Okay, so then you end up with two integrals. 2 gamma wave function, delta function. And again, this is so awesome because I can already see this is 2 gamma wave function at 0. Right? Remember in your homework, delta function's job is to wipe out integrals, and whatever is on the inside of the integral is left behind at x equals 0. So that's easy. Okay, and then I'm going to subtract out this thing. And again, there's a trick to this. K squared Okay. Okay, now there's a trick. What's the trick? This is the area under the curve of a number. So we take that out. And a wave function. And we're assuming that the wave function is behaved. It doesn't fly off to infinity. It's not zero everywhere. So what do you think the area under a curve is when that width times height? What do you think the area under a curve, any sine, cosine, is when the width is infinitely narrow? Huh?
Zero.
Yeah, just zero. Right? So anyway, there's the trick. That's just zero. And hopefully that's just kind of obvious. No proof necessary. I look at this and I kind of want to do a proof of some kind, but no, that's what's really the limit doing that. So that's one thing that when we do this kind of stuff in chemistry, we often end up using a lot of just like horse sense, right? We happen to know that this is the answer. Okay, so therefore this ends up being, let me pop down here, 2 gamma, wave function is 0. And here for symmetry purposes I'll do this. Okay, so now here's what you get out of that. And again, this is basically identical to your homework. God, this is so neat, don't you think it's neat? Is that I just got the derivatives of the wave function equal to the wave function at point 0. That's all there is. And I probably need to put limits here and there anyway. Okay, so now what is that? Oh God, this sucks. Let's see. Now I'm going to make sure I know what I'm doing. Okay, so let's go for epsilon -0. Sorry, how do I want to do this? Yeah, so sorry, for negative epsilon going to 0, what I mean is the left. So we're going to analyze this for the left side. Okay, what's the derivative? The derivative of the wave function. Now, the reason I'm doing the stipulation is that I'm using the a e to the ikx plus b e to the minus ikx. Right, so you need to make sure that you keep left and right, because one is a and b and the other one is c. On the right is c. Okay, so now again, if you look up there and see what my wave functions are, a is 1, so but the derivative is ik e to the ikx. And remember that x will be 0. B is, we don't know what b is. Okay. And then since we're now invoke the limit, you've got ik 1 minus b. Okay. Now, on the right side, so we just did, we did this one, right? So now let's do that one. I should have done this the other way, shouldn't I? So for the right-hand side, so now we're solving this, by the way. So I should have done this one first. It actually just makes more symmetry, right? Let's see, what do we got? Oh, the derivative of the wave function is stupid simple, ik c e to the ikx, and that x equals 0 is just ik c. Okay. So what you end up with is, make sure I'm doing this right. Okay, so this term, let's do that term, ikc minus ik 1 minus b is equal to 2 gamma. Okay, the wave function at 0, we can actually choose whether we want to do which form we want, the left or the right hand side. So the wave function at 0, if we chose the left side, is just 1 plus b. If we choose the right side, it's c. Now, here's what I'm trying to do. I'm going to pick one or the other to figure out, because I'm going to try to get to what I'm solving as fast as possible. And what I'm trying to do is I'm trying to solve for b in this case. So I'm going to choose the left-hand side, wave function, 1 plus b. And just recall that psi is 0. And I'm going to do this again, and I'll solve it on the right side. I'm solving for b now, and I'm going to set this up again to solve for c, and then I'll use side 0 on the right side. Because again, I've already worked through this, it's faster. Okay, next thing is, you recall from step 2, that c is equal to 1 plus b. So therefore you've got ik 1 plus b, see what I mean? Minus ik 1 minus b is 2 gamma 1 plus b. And as usual, now we're in an algebraic hell. It's not too bad. Therefore, b is gamma over ik plus gamma. There you go. And that's our reflection. Actually, that's not the reflection. Remember, this is the percent reflection. Therefore, the percent reflection, which is the absolute value, and hopefully, again, you know to multiply this times its complex conjugate. I'm relying on you to know enough maths to be able to do that. It's not too hard. Remember, so technically, we can still do in-person office hours if you feel like. So it looks like this. It's actually kind of intuitive. So there you go. There's a reflection, and as I mentioned, this is basically identical to your homework. And now let me do transmission. And I'll do that. I'm going to start from here. I'll start from here, so I'll just wipe out. I'll wipe out our drawing right here. You don't really need this anymore. Okay. Actually, you can actually solve for C. You can actually solve for C right there. Hell, that would be easier, wouldn't it? I'm going to write this down just for your own practice. I mean, technically, you could just put C as C minus 1 is B, right? And then you can solve it. Yeah, of course. I mean, transmission is 1 minus reflection. You actually have a couple of ways of solving this at this point. We're pretty much done. Just for the heck of it, I just want to show you that if you actually did this from the other side, so remember I kind of did this on the left-centric basis, but if you did right-centric, let me just show you what that would turn out to be. If you did, okay, so here's the derivative of the right side, the upper limit to the integral of the double derivative, minus the integral of the right side, of the left side, the lower limit of the integral of the double derivative. And again, here, the wave function at point 0, if we went to the right, is just this. And then you use b is equal to c minus 1, and that's from yes. Where did I do that before? Yeah, from point 2. Yeah, from right here. God, is that right? Yeah. Then what you end up with is IKC minus IK, minus plus IK, C minus IK is 2 gammas, 2 delta C, right? I keep calling it gamma. Okay. What's bothering me is that my C's look like parentheses. Anyway, bunch of algebra later. Hopefully I didn't mess that up because I'm actually, my eyes are almost literally cross-eyed because of how similar my C looks like a left-hand bracket. Okay, so C is this, and therefore absolute value of C squared is K squared over K squared plus gamma squared, which if you added this plus that, you would have gotten number 1. Hopefully that's obvious. So this is percent transmission. Oh, I didn't write that down. Oh, yeah, no, I did. So, of course, this is percent transmission. And the way that looks, God, I'm all over the board, aren't I? I do look at the video sometimes. Anyway, if you look at K, so on my axis here is K, and you know that that's increasing energy, right? So I'm just putting it in a slightly easier way to calculate. The lowest reflection or transmission we can have is 0, the highest is 1, and if you plot this, you see something like this. Percent transmission, and the percent reflection, of course, is exactly the mirror image. Anyway, hopefully really quite straightforward. Now, the point of this was, again, it's a little bit of a math exercise. Oh, it bothers me that T's right, there we go. Okay, now the world will blow up. Part of this is a math exercise, and we value mathematical ability in physical science. It also is a setup for your homework. You get to use the delta functions, and delta functions are awesome. Now we're kind of doing more graduate level. But now here's the real thing. There's actually, I have kind of a hidden agenda here. What I'm not saying is behavior I would call a resonance. Now, a resonance would manifest itself as wiggles in the transmission and reflection. Why is that important? It's because quantum phenomenon manifests itself in, let me default to like Argonne National Lab type work, because again, I think, several of you might end up working at Argonne. When you look at X-ray absorption, X-ray through a material, and that would be, absorption is basically just, you can relate absorption to percent transmission. They're functions of each other. So an absorption of like really high means 0% transmission. An absorption of 0 is 100% transmission. When you shine X-rays on atoms, you see wiggles like crazy. And you can only understand them by resonance phenomenon. Now, you're not seeing that here. But what I've got is a really crappy model for an atom. That's the world. A delta function barrier is not an atom. Atoms have finite width. Okay, so what I want to do now is I want to modify this model. I want to put in 2 delta functions. Because, for one, I happen to know we're going to start to see resonance phenomenon. Number 2, it's starting to, we can make the 2 delta functions like it's about as big as an atom. We can do that. It's also a good math exercise. It's good at this. And like I say, we'll see resonances. And I will show you how to solve this freaking problem on a computer. So hopefully, with this exercise, I think the hard part was realizing that you needed to use the Schrodinger equation and integrating it over a narrow limit, and not trying to do anything too funky with the double derivative, just turning it into the 2 single derivatives, upper and lower limit. That's the trick, in all honesty. Now that you know that trick, let's do a harder problem, which is, of course, as I mentioned, we're going to still have one potential at 0, and we'll have the other one at A. 2 delta functions. So we're going to have region 1, region 2, and region 3. Okay. And like I say, what's going to be kind of awesome about this is that you're going to see resonances. Yay! Oh, you don't care. Okay. Now, hopefully, I've set you up that I'm just going to spit out some of the factoids of this problem, and hopefully you're like, yeah, sure, whatever. Okay, region 1, we're going to have e to the I kx. Again, A is 1. B, the reflection, I'm not too sure about that, so it gets a letter. Of course, it's moving backwards, so that's minus I kx. Region 2 is going to be the same, except that it's got a C and a D, so we've got a C wave and a D wave. backscatter, and so this is within the trap. One reason I like this problem is that all the k's are the same. When we do the finite barrier, and we're not actually going to do it because that one's really a suckfest. The k's are not the same in the different regions. Here they are. Okay, and again, we assume that if the electron is going to get through both barriers, then it's just going to continue to move to the right. So that's e to the ikx, so that's our E wave. Okay, so let's see here. And I want to make sure that this makes sense. I've got two equations for continuous at the two boundaries. One thing I can see is I love having x at 0, having a boundary condition there, because e to the 0 will be 1. But, yeah, so it's going to be a little bit harder because I have an e to the a, and that's not going to just disappear. So that's going to be a little bit harder. Okay, I've got two equations, then I got two Schrodinger equations that I'm going to integrate in that funkified way that you just saw. So I've got four equations, and I've got B, C, D, E, four unknowns. Four equations, four unknowns. This is done. It's just a matter of plowing through all this stuff. Let's just do that.
If I cross any potential?
Well, no, sorry. The potentials at 0 and A are identical. So that's 2 gamma, h bar squared, 2m over h bar squared. What's wrong? It's the same as last time. There's just two of them. Let me make sure I write it down right.
The second is not potential, right?
Wait, h bar squared over m gamma. H bar squared over. Delta. And that's at x equals 0. And it's also h bar squared over m gamma at delta function of x minus a. So yeah, you have two of them. Yeah, I need to be more careful. Yeah, I've worked through this. I spent about 2 hours working through this problem in the notes. So like in my head, it's like perfectly clear. Anyway, and yeah, this one ends up being a little bit harder because instead of a 0, you have an a in it. It's not too bad. Okay, so anyway, so at x equals 0, what have I got? I've got psi 1 is equal to psi 2, therefore 1 plus b. See, it starts out in a very non-threatening manner. Okay, now what? Okay, so now let's go ahead. Now I'm assuming that you recall from 10 minutes ago how you do the integration. What you've got is you've got the derivative of region 2, the upper limit of that integral of the double derivative minus the derivative of region 1, the lower limit of the integral of the double derivative, and that would be equal to 2 gamma wave function. And I'm going to choose region 1 at 0. And so this ends up being, okay, on the integral on the right side, it can be ik c e to the 0 minus ik d e to the 0, that's 1. Okay, so that's this part. Then we're going to subtract the integral on the left side, and that is ik 1 minus b. Remember, a is actually 1. I could have done this, right? This would have made your life a little easier. It looks more similar, right? Now they look more similar, except that this parentheses is not as big, and that bothers me. There we go. Now it's perfect. All right, so we've got that, and then this is equal to 2 gamma, 1 plus b, again at the right side. Next we do at x equals a, of course, region 2, the fact that it's continuous means that is true. And therefore, C e to the I k a. So yeah, this is where it starts to be a little bit more difficult. And as I promised, for those of you who were here early, I'm actually going to do this on a computer. I'm going to solve it on a computer. And what you can do is, one of the tricks here, by the way, you can actually multiply this whole thing by e to the minus IKA. So I just want to point that out. As long as you multiply both sides, and it ends up being way easier. You've got C plus D e to the minus 2 IKA is equal to E. Okay, so right, not nearly as bad. So no, remember, we've got to get we have 4 unknowns, 4 equations. So this one, this one, this one. I mean, it's not that bad. And then, of course, the last one, the double derivative in region 3. The single derivative in region 3 minus the single derivative in region 2 is 2 gamma wave function. And I'll pick in region 2 at A. And what that means is that in region 3, the derivative is IK e to the IKA minus the region 2 derivative, that's minus IK, and I'll factor that out. That's C e to the IKA minus D e to the minus IKA. And that's equal to 2 gamma. Again, I'm going to choose the left wave function. Remember, it's not the derivative of the wave function, it's the left wave function at A plus D. D is a left wave, so it's going to be minus IKA. Okay, and this is a little sucky. No doubt. Okay, so let's see again. 1, 2, 3. 1 and 3 don't look so bad, and this is 4. 1, 2, 3, 4. System of equations. Yada, yada, yada. What do I want to do with that? I am not going to sit here and do 20 days of algebra on this. I'm going to solve this on a freaking computer, because what the hell? And I want to see how you do that. So what I'm going to do is I'm going to plug these 4 equations into a computer and say, hey, solve it. And what it's going to do is give me A, B, C, D. So let me show you how I do that. And I use Matlab, and
Alright everyone, so it seems that the camera did not really do a good job capturing the what I was doing with Matlab on the screen, so I'm going to just record what I'm doing on my computer. You should be able to see that a lot better. You can also check out my Tinder profile. Anyway, so here we have Matlab, and hopefully you can see what I'm typing. I know it's a little difficult, so maybe I will increase the font size a little bit so that it's a little easier to read. Okay, now what I typically do is we're trying to solve the system of equations for the problem, the double delta potential, and of course we have 4 equations. 1 plus b is equal to c plus d, yada yada yada, what we just did. And now we 4 equations, 4 unknowns, we want to solve them. The algebra would seriously take about an hour, so I'm going to have the computer do it. Now, and in all things, whenever I'm trying to figure out how to do this, Matlab can do it. I go into Google, Matlab, solve system of equations, and here we go. Yep. Alrighty, let me zoom in here so you can see that. So it's exactly what I need. Here's it's making sure that you know what a system, making sure you know what this is to begin with. A plus b is 1. A minus b is 0. Okay, it's reminding you of that. Now, hopefully in high school you learned that you can solve systems of equations with matrices. Okay, so I know that. All right, now here's the example, and I'm just going to rip off the example. Here's a system of equations, and here is the Matlab text for solving it, and I'm just going to basically use this for my own purposes. Sims XYZ, now that is called a symbolic declaration to Matlab, letting Matlab know that X, Y, and Z are not 5, 6, and 7. They're undefined, and MATLAB's job is to define them, so it understands that. Okay, this next part, equation 1, 2, 3, it's kind of easy given the nature of the problem. It's the same as the problem. Then we have this command, AB, equations to matrix. I'm not totally sure what that's doing. I'm well, it's turning it into a matrix form. And then it solves it. X is linsolve AB. And here are the solutions to that system of equations, X, Y, and Z. So I'm just going to subvert this for my own purposes. Okay, here's MATLAB. First thing I always do is type clear all. I'm going to make my declaration B, C, D, and E, just like in class. Okay, I need to remember that there is a k, or square root of 2me over h bar squared. E is energy, and it's not the other e. Sorry, there's two e's, I know. Omega for the strength of the potential, the delta potential, and a is the distance in between. So there we go. Now I just need to type in the stuff. Okay, equation 1 is, so it's 1 plus b is equal to c plus d. It tells you when you did something wrong, so I appreciate that. Double equal. By the way, if you don't add that semicolon as you get to know MATLAB, what it does is it just repeats what you typed. It's like so you know. Okay, equation 2 is, all right. You know what? I'm gonna type this all out. This is exactly what you did in class. I'm gonna speed it up, so I'm gonna increase time on the video deal. Alrighty, so now that I've typed all those out, it takes a while. I don't really quite understand what the MATLAB is doing, but I don't really need to. I'm just copying from that website. FU, that's fitting, is equal to equations to capital T. It matters. Now we're letting it know. Equation 1, 2, 3, 4. Now this next part is telling it what it's solving for, and you're solving for B, C, D, D, and E. Okay, that's it. X equals linsolve. Okay, now what I know is that this gives me what I'm looking for, so I understand that. There we go. Yeah, this is literally it. Here is what our B coefficient. So if I square it, then that's the answer. That's my reflectivity. B, C, D, E. So here's my transmission. If I square this. Now practically, note that I'm going to have to define K. I is just the square root of -1. Omega, I have to plug in a value for omega. A, I have to plug in a value like 1 nanometer. I have to make sure all the units are SI. But regardless, this is the answer. I know it looks like a mess, but this really is the answer. And we can start plotting it. But again, you know, if you're going to plot something, you really got to be working with real numbers. I mean, you have to. And to do that, again, you've got to be defining K. So we can plot like energy from 0 to some big number like 10 eV or something. And that defines K. Given that we have a mass, we'll make the mass 1 electron. A will be 1 nanometer. It's all quite sensible. Okay. Now, as I mentioned, I actually have, I've already written all this out. So I want to show you what else you can do with this. Let's see here. I am going to plot the E squared, the percent transmission, as a function of energy, given those parameters I just mentioned. Now this is a bit of a pain, so I'm clearing everything. Mass, you see the masses of an electron. I have to define h bar in proper units. Again, I'm making the double delta potential barriers 1 nanometer apart, defining what an electron volt is, making sure that I is the square root of -1. Okay, so I'm gonna send all this to you. I just hit enter, and it's gonna plot. And there we go. All right, now the x-axis is in units of electron volts, and I defined omega in such a way that you could see these resonances. And here's what I was talking about. Here's those resonances I was telling you about, where at certain energies the electron will pass through this barrier with 100% certainty. And it's just the thing that is just kind of shocking about all this. I mean, maybe you don't have enough of a background in classical mechanics to say, wow, this really should not be happening. And by wow, this shouldn't be happening is once the electron has enough energy, let's look right here around 1/4 eV, once the electron has enough energy to pass through the barrier, it ought to continue to do so. But no, it doesn't. So as it speeds up from 0, it all of a sudden has a certain energy to pass right through the barrier, but then the probability it bounces off suddenly increases, hence a drop in transmission. Then it goes up again. All of a sudden it passes through the barrier no problem, and all of a sudden if it has more kinetic energy, it's actually more likely to bounce off of it, which is, I mean, that's absolutely bizarre. If it has enough energy to punch through, it ought to always have enough energy to punch through. That's like more true if it has more energy. But that's wrong, and that's why we study quantum mechanics. Now, I also want to point out that this behavior, we see this all the time when we study electrons, but we're chemists, we study electrons. We see this type of behavior in X-ray work, like with what's called XAFs, extended X-ray fine structure, which is the probability of ionizing a material as a function of energy. You get wiggles just like this. And it's also a scattering phenomenon. Okay, next thing is to understand what is special about these energies where you get 100% transmission. Now, it just, you can look at this as like, well, it is what it is, but here's the secret. If you plot the solution to the second area, we have areas 1, 2, and 3, and area 2 is the space between the two double delta potentials. If you plot those wave functions at corresponding to these energies, then you're going to learn something. Now, the program to do this is a little bit much. I have to admit that. So I'm just gonna type this here. So I'm going to type it out. It's a bit of a handful to see what I've done, and I'll send it to you, and you can try to figure it out if you feel like. Here's the result, and the area between 0 and 1, it's in nanometers. The area between 0 and 1 is the area between the two double potentials, double delta well potentials. Okay, let's zoom in, and now I think you can understand a little bit better why this is happening. These are basically particle-in-a-box wave functions, right? So it look just like it. No nodes, one node. It looks a little funky because I'm plotting the absolute value of the wave function because the wave functions are complex, but they are particle-in-a-box wave functions. So that is kind of satisfying in a way, but we can do a little bit better. Okay, so why particle-in-a-box wave functions? Why is it that an electron has just the right amount of energy to be like a particle of box between the two double delta potential barriers? Why does that work? Okay, the answer is a particle in a box has nodes at the endpoints, right? That's where the wave function is 0. Okay, so again, if the electron has just the right amount of kinetic energy, such that it naturally has a node at 0 and 1 nanometer, it, for one, looks like a particle in a box, because again, that's what a particle in a box is. It has nodes at the endpoints. But if it has a node where the barriers are, then it doesn't really experience the barrier, right? It doesn't exist at the barrier, therefore the barrier doesn't exist. So that's why it just slips right through. Okay. Anyway, with that's really all there is, and mostly I hope that you get something out of all this, something practical, right? Because you may end up needing to use this type of stuff. I don't want this class to be just completely, just you learn some things that are never practical. Now, normally I end with a robot or an explosion, but today I thought I'd end with kitties. So there's my Charlie, there's Zoe, and here's Zoe in the morning. This is on my website, by the way. So this is what I wake up to every day, and this is before I had to have her tooth out. If you look at her face, you can actually see one of her teeth is sticking out, and it turns out that she had a bad tooth, so I had to take her to the vet and have that taken out. Oh, look at that. Let's see, what else have I got? Okay, they're just lying around, being lazy. There's Zoe in the sock drawer. She knows she's not allowed in there. There's Charlie sitting on my chair. Okay, with that, I think I've seen enough, so we should just sign out. So anyway, okay, with that, we should definitely sign out. All right, so I'll see you all in class. Anyway, okay, with that, we should definitely sign out. All right, so I'll see you all in class later. Bye.